what I want to do is kind of spend about 20-25 minutes on the spectral part, particularly the harmonic processes, and then briefly talk about spectral factorization. If you recall, yesterday we were talking of harmonic processes, which are random processes that have a periodicity in them. And as I mentioned yesterday, there are different models for harmonic processes. One of the standard models is sine embedded in noise. So, for example, you could think of V being made up of a cosine plus some Ek, where this part is completely deterministic, there is no randomness in them, and discovering the frequency omega naught from measurements of Vk is a classic problem of the sinusoids embedded in noise, discovering measurements from sinusoids embedded in noise. And the problem with this kind of a model is that Vk is not stationary. Nevertheless, this problem has been widely studied and there are numerous solutions that are available, and a fantastic book which is very easy to read and also gives you a very nice historical account as well as good insights into the different solutions that have emerged and generalizations of this model is the book by Bloomfield, which is one of the most widely referenced books, and in fact I do give this as one of the references towards the end of this lecture as well. So, do read that book, it is a very nice book, very easy to read, no complications, begins with a very elementary material to begin with. Now, we will not pursue this model per se because we are dealing with stationary processes. This model is not amenable to stationarity. Now, gradually people said, well, why do I have to consider a mixed model like this? I would rather consider another model, which is, as I wrote yesterday, simply consider Vk as A cos omega naught k plus V. There is nothing specific about cosine, you could even have a sine. Here there is nothing about no sanctity about using a cosine function here. But the difference between this model and this model is now we can allow phi to be random, okay, and in addition we can also have the amplitude to be random. Okay, so yesterday I did mention that amplitude could be fixed, but in general you also let the amplitudes be random. That is the size of the sine or cosine that you are using to synthesize the periodic random process, as well as the phase, that is when a particular wave sinusoidal or your building block begins with reference to the signal also can be a random variable. Now, you have to understand that A and phi are random variables, while V is a random process. What is making V random? The A and phi are making Vk random. A and phi do not change with k, that is something that you have to understand, right. So, what this means is for one realization A and phi are fixed. The different possibilities of A and phi, as you span across, as you walk across the space of A and phi, that is a sample space of A and phi, you would have generated an ensemble of Vk. Of course, you know, walking along time as well. So, you have A phi giving the randomness in Vk, whereas here the randomness is imparted by this white noise. So, depends on what model you are looking at, and that is something that you should keep in mind when you are analyzing a random periodic process. Simply do not jump to using periodogram or any other tool. First spend a moment and ask what is the model that you are imagining for the given signal, and so is the case with the aperiodic process as well. What is the model that you are imagining, whether you are looking at an AR model, MA model or an ARMA model, and so on, and then you decide to fit a corresponding model and then you draw the necessary inferences. So, here when you assume that A is a random variable and so is phi, you given measurements. Now, the problem is that you are given measurements of Vk and we are supposed to estimate, let us say A, omega naught and phi. These are the three parameters that we are supposed to estimate for a given realization. Whereas, in the previous problem you are given Vk, again the same story, what is given to you is the same, it is always the finite length data record. But what you determine here again is A omega naught on phi and phi, but in addition you may have to estimate sigma square E. The only difference is A omega naught and phi are deterministic. Here A and phi are random, omega naught always remains fixed. Of course, you can have multiple frequencies, a sum of cosines and so on. Now, what happens is in general, when you are trying to estimate, let us say A and phi, given measurements of V, you could actually pose this as a regression problem. Okay. You could pose this as a regression problem. What we mean by regression problem is, suppose I expand this, I have here A cosine omega naught k and sin phi times sin phi plus A, what do we have, have here cosine phi plus A sin omega naught k sin phi. This is simply by trigonometric expansion, is that right? So, now if you look at from a regression viewpoint, let us say I give you omega naught, you kind of know the periodicity and then the goal is to determine A and phi, that is amplitude and phase. You can pose this as a regression problem. We will shortly learn how to detect omega naught. In fact, we have already done that, we look at the power spectrum. Here you would look at the power spectrum as well, but the only difference is you are looking at random signals. So, let us say you know omega naught, then you can construct, you can consider regressing Vk onto two regressors, cosine omega naught k and sin omega naught k, right. And then you would try to estimate A and phi, or you can just say, well, find A and phi such that the standard optimization problem is solved, expectation of Vk minus A cosine omega naught k plus phi whole square, that variance is minimized. Or you could solve the sample least squares problem, you could say minimize Vk minus A cosine omega naught k plus phi whole square, k running from 0 to n minus 1. This is what you would be solving in practice. Whether it is this model or this model, you will be solving this optimization problem, right. Now, the point is, when you use this model, the decision variables are A and phi, you have to optimize them. And you look at the regression problem, is it a linear regression problem in the unknowns or a nonlinear regression problem? It is nonlinear. We want to avoid nonlinearities as much as possible. So, can we now convert this to a linear regression problem? What do you think? How do we do that? So, we can now denote A cos phi, right. Let us actually rewrite this. We can say A cos phi times A cosine omega naught k. Likewise, here we write here A sin phi sin omega naught k, and now denote this with some A naught and this by B naught, right. Instead of estimating A and phi, I am going to estimate A naught and B naught, and that makes the regression problem easier. Of course, in this case what I would do is I would indirectly estimate A and phi, but if I just want to know what are the contributions of cosine and sines, I do not need to go back to A and phi. How do I recover A and phi from A naught and B naught? Simply use a trigonometric identity, right. Trigonometric identity is A would be square root of A naught square plus B naught square, and phi would be simply tan inverse B naught by A naught. Of course, that is a nonlinear mapping, there is no escape to that. All we are saying is, instead of solving a nonlinear regression problem, let me solve a linear regression problem. The problem at the time of estimation is simplified. Now, from A naught and B naught, if we truly want to recover A and phi, then we have to go through a nonlinear mapping. But if you do not want that, then this is a much simpler model to work with, and that is exactly what you see on the screen. Except that now we have generalized, only that we have generalized now this idea to a mixture of cosines and sines. I mean, you could have multiple periodicities. And now a n, that is a small a n and small b n, are random variables, given that already a is a random variable and phi is a random variable. And generally you can show that if phi falls out of a uniform distribution and a has a chi-square distribution, then you can show that small a n and b n follow a Gaussian distribution. Okay. Now, we did discuss additional requirements on a n and b n for V k to be stationary. Remember, we want V k to be stationary, whereas this model does not allow V k to be stationary. So, we will discard that model in favor of this one. And what are the conditions that we imposed on a n and b n? The first condition was that their averages should be 0. And again here we are talking of averages of a n and b n within their respective sample space. You have to understand, there is nothing, there is no notion of time when it comes to the coefficients. For a given realization they are fixed. Notice that there is no dependency of a n or b n on k, they do not change with time. For one realization they are fixed. Again another realization, a n and b n would take on another value. So, the requirement are twofold. First, a n and b n have to be independent random variables. There was a nice question asked by one of the students yesterday when I said a could be fixed and phi alone being random, then how could you guarantee independence, and that was correct. But now we have corrected that by saying a should also be a random variable, and now you can afford to think of a n and b n being independent random variables. Independent would essentially mean here uncorrelated, that is, of course, independence is a very strong requirement, but a consequence of independence is uncorrelatedness. So, you are given that a n and b n are uncorrelated. What does it mean? The way I choose a has no bearing on the way I choose b. The cosines and sines can add in their own way. Just because I included a cosine of a particular magnitude, it should not mean that a sine of similar magnitude or a related magnitude should be included. They can be on their own. And with equal, of course, you assume equal variances, they do not have to be equal variances, that is only for convenience sake we assume equality. So, two requirements, independence and 0 mean. With that assumption, you can show that the autocovariance function is simply what I have given you on the screen. It is sigma, that is the sum of sigma square n. In fact, sigma square n is the variability of a n and b n. When we said equal variances earlier, for a given omega n, a n and b n have equal variance. Now, how do you arrive at this expression? Well, fairly straightforward. First you derive the mean, right. We know already the mean is 0 because a and b have 0 averages, the small a and small b, and then you apply the definition of autocovariance function and use the property of trigonometric functions. Using that, you can show that the autocovariance function has a Fourier series expansion. As I remarked yesterday in the previous lecture, the ideal situation should have been that you should have complex exponentials in the Fourier series expansion, but because autocovariance function is symmetric, you only have even functions participating in the Fourier series expansion. So, what it says essentially is now your model is indeed generating a harmonic process, right, because the definition of a harmonic process is that the autocovariance should be periodic with the same period as the signal itself. And here indeed, of course, in this case the period, what would be the period when you have a mixture of cosines like this? The least common multiple, right, and that is important. So, your omegas or your f should be such that there should be a least common multiple and you should have an integer period, all of that is implicitly assumed. Okay. So, that is it. So, we have guaranteed that this model generates a stationary periodic process, in other words a harmonic process. You can come up with your own models and so on, but as far as harmonic process is concerned, this is by far the most widely used model. And in practice, we would be given realization, a single realization of Vk, and the goal would be to discover omega naught, and of course, the coefficients an and bn, they are estimates, point estimates only from the given realization. Okay. Now, of course, that part we will discuss in the estimation part, but what we now can remember is that for a random periodic process or a harmonic process, the ACVF has a Fourier series expansion, whereas for an aperiodic process, which is what we have discussed at length, the autocovariance function has a Fourier transform, and that there it would give us the spectral density. Here we do not get a spectral density at all. And just for comparison, you should you should observe that in the deterministic case, the squared magnitude of Fourier coefficients gave us the power spectrum, if you recall, right, of the Fourier coefficients of the signal expansion. Whereas for random signals, the expectation of the square of Fourier coefficients gives us the power spectrum of the random periodic signal. What we mean by this is, if you go back to this expression here, you see that you have sigma square n as the coefficients of the Fourier series expansion, correct. And what are these sigma square n's? They are the contributions of the individual sinusoids or cosines, you can say, to the overall power, right. In fact, how do you say it is a contribution to the overall power from this expression? How do you say that? Exactly. At lag 0, what is the expression that you get? Sigma square V is simply the sum square sigma square n, correct. So, this is what you would have, sigma at 0, this is for the signal, to be more specific an or bn, I mean just to highlight that this sigma square is for the coefficients. And we know already cosines and sines give you they are orthogonal functions. So, each contribution is unique. So, we have now a power spectral decomposition. Look at the difference here. In the deterministic world, the moment we move to aperiodic signals, we always talked about energy signals, whereas in the random signal world, whether it is aperiodic or periodic, we are always talking about power. The fact is and the reason is because they exist forever. I mean, the signal never decays with time, even if it is aperiodic. So, in both cases it is power, you do not have to be confused at all. And in fact, when you use DFT also, it is always empirical power spectral density that you consider. So, everywhere it is about power. The energy spectral densities kind of take a back seat when it comes to practice. So, this equation tells us that the power of the signal is decomposed into the respective contributions from the frequencies. They need not be necessarily here kind of harmonics, okay. You just have some bunch of frequencies adding up. All right. So, now that is what gives us this interpretation that we just made, that for random signals the expectation of the square of Fourier coefficients. When I say square of Fourier coefficients, the Fourier coefficients are actually an and bn, remember. The only difference is in the deterministic world, those ans and bn's would have been fixed or deterministic, whereas for the random signal ans and bn's are random variables. Remember, we made this observation earlier also. So, that is why we are talking of expectation of square of Fourier coefficients. So, that is the difference, always the expectations come in for random signals. Anyway, so now we kind of unify everything whatever we have looked at until now, that is the world of aperiodic signals and periodic signals. In the case of aperiodic signals, we talked of spectral densities, correct, and when it comes to harmonic processes, we talk of power spectrum alone. Of course, I have shown you a number of signals and so on, but one thing that I will show you in R is the use of ARMA ACF, which will allow you to compute the theoretical spectral density. But I reserve the discussion on estimating power spectral or on working with real life examples to the session where I will talk about estimation of power spectra or power spectral densities, and at that time we will take up some real life examples and at least real life data sets and show you how to interpret the resulting power spectral density and so on. Okay. So, the to summarize, what we have is for aperiodic signals we have power spectral density, and for harmonic processes we have power spectrum. Again, this is an analogy with the random variables. For continuous valued random variables we have a probability density function, whereas for discrete valued random variables we have probability mass function, correct. But regardless of the situation we have a probability distribution function. Likewise here, whether we have a spectral density or not, we will have a spectral distribution. We can think of a spectral distribution function. Of course, for an aperiodic a stationary process, you can write the spectral distribution as an integral, as an area under the spectral density, and that is what I am pointing out, exactly like your probability density. If you are confused, just recall the probability density notion, right. Whereas the spectral distribution for a periodic process will not have this kind of a or a harmonic process will not have this kind of a relation. There is no spectral density at all. How will the spectral distribution look like for a periodic process? Step like, right, whereas here it would look continuous. Exactly the same case as you see in the probability in the random variables. When you have continuous valued random variables, this probability distribution would look continuous, and for discrete valued random variables the probability distribution has a staircase like shape. Okay. So, now with this we just study the unified Wiener-Khinchin theorem. There is nothing new in this. All we are doing is we are unifying two results, one for the aperiodic case and other from the periodic case, and this is basically on the lines of Fourier-Stieltjes integral. If you recall, we said there is a Fourier transform for aperiodic deterministic signals, finite energy signals, and then there is a Fourier series expansion for deterministic periodic signals. And then if you recall, we said the Fourier-Stieltjes integral unifies both those results, so that it becomes easy to look at both class of signals in a single framework. Likewise, this unified Wiener-Khinchin theorem unifies the relations between autocorrelation, or in fact here this autocorrelation, and the spectral distribution now. So, what this result says, and this is a very profound result in the theory of random processes, it says a discrete time stochastic process, or sorry, a discrete sequence rho of L. So, I give you some sequence, and if I want to claim that it is the autocorrelation function of some stationary process, it is true if and only if you can associate a distribution function f of omega such that rho of L is this integral. So, what it says is you pick any sequence, discrete time sequence, and you can claim it to be the autocorrelation function of some random process. So, if I were to ask that question, why is this important? Because in practice what I have is a realization, and I am going to compute autocorrelation function, and I have to be guaranteed that from this autocorrelation function that I estimate, I will be able to construct a model that will generate a stationary process. So, what guarantees me that? This theorem says if you can construct a sequence, if you estimate the autocorrelation function in such a way that you can associate a distribution function which is related to this autocorrelation function in this fashion, which is called again the Fourier-Stieltjes integral type of thing, then essentially the sequence that you have rho of L qualifies to be the autocorrelation function of a stochastic process. This includes everything, symmetricity, non-negative definiteness, everything is embedded in this. How is it embedded? Because this distribution function, in fact, because we are talking of autocorrelations, is a normalized distribution function, should have some properties. what is meant by distribution function you should ask, and what qualifies to be a distribution function. Some of the qualifying most qualifying remarks are given here. First is it should be non-decreasing. We said the same thing of a probability distribution. What are the qualities of a probability distribution function? It should be non-decreasing, right, over the extremes. Here, because it is spectral distribution, the extremes are minus pi and pi, whereas in the probability distribution case, the extreme values for the random variables. So, in other words, I cannot the distribution function, for example, has to look something like this. It cannot, your spectral distribution cannot look like the other curve. So, I am only drawing for the 0 to pi. Sorry, I should have drawn from minus pi to pi. I'll just redraw. So, let us say here is pi and here we have minus pi. So, what this says is the distribution function, if you are looking at a periodic process, has to be like this. Okay, so, it has to run from minus pi to pi in a non-decreasing fashion. You could also have a staircase like signal, in which case you are looking at a periodic random process, harmonic process. Moreover, it is normalized. What does it mean? What does normalized spectral distribution mean? At pi, it should reach a value of 1. It is normalized. What is it normalized with? The variance of the process. That is why we have the autocorrelation, and then it should be right continuous and it should be bounded. So, all of this actually makes constitutes a normalized spectral distribution function. So, if I give you the a sequence and I claim it is the autocorrelation function of some process, or if I claim that there exists a process whose autocorrelation function is what I give you, then necessarily the autocorrelation function should be expressible as this integral. A simpler way of looking at it is, you should be for a periodic process, if I tell you, if I give you a sequence and I claim that it is the autocorrelation function, its Fourier transform should exist for an aperiodic process. For a periodic process, a Fourier series expansion should be possible. That is what it means. Okay. So, it just unifies this. So, this is kind of a summary of so many things that we have learned in a single theorem, but and that is why it is a very profound theorem, because obviously people were asking these questions. Okay, I have this definition of autocovariance, autocorrelation, then I have this definition of spectral density or distribution, and then I have to worry about I have to guarantee that there exists a stationary process for a given sequence. All of these questions, how can I guarantee and so on? This theorem answered all those questions, and it says yes, this is how you guarantee, right. Of course, the proof is a bit involved, we do not go through the proof, but it is very important to remember this theorem. And I have already talked about the normalization. The normalization essentially is with respect to sigma square.